I'll share all the links in the
in the
chat
chat box.
box.
Thank you. So now I invite our next resource person for the day. Mr. Hartinder Kumar. PGT Physics from Bharati Vidya Bhavan Public School, Amritsar, with a total teaching experience of 27 years. He has been awarded the Bhavan Jindal Award for the Best PGT 2012 and CBSE Best PGT Physics Teacher 2018. He is a CBSE resource person. He is a guide teacher for National Children's Science Congress, CBSE Science Fair, Inspire Award, National Innovation Foundation for the past 27 years. So over to you, Hartinder sir. A very warm welcome to you.
Thank you, Inu ma'am.
Thank you, sir.
Good evening, everyone. Namaskar. I welcome you all to the Faculty Development Program for the Science Educator, organized by Section Bharati, Bharatiya Vidya Bhavan, Delhi Kendra. My sincerest gratitude to Dr. A.K. Sharma sir for providing me this opportunity to interact with the science educators across Pan India, where we can discuss that what are the latest pedagogies which we can use in the class to meet the vision of National Education Policy 2020. With the permission of respected Dr. A.K. Sharma sir, I'm going to start my session on the topic magnetic field produced by current carrying conductors for the class 10. So today's session is based on magnetic field due to current carrying conductor. So we all will share our views on this topic. What are the different pedagogies which we can use to make the concept of this topic clear to our learners? And we will also discuss the various type of activities which we can perform to make the concept clear. My dear friends, the Ministry of Education has introduced National Education Policy 2020. And as per the instructions of CBSE and Ministry of Education, all learning instructions, all teaching learning processes should be aligned with the vision of NEP 2020, which says to provide an education to all means to all, which is a blend of 21st century skills and great Indian ethos. My dear friends, the world is changing every second. In the coming 5 years, the new professions will come, whereas the older ones are disappearing. The technology is changing every moment. And if we want that our children should survive in the next 5 to 10 years, then they must possess the 21st century skills. Not only 21st century skills, but the great Indian ethos also. They must have a strong value system. The Ministry of Education has identified 3 skills as a 21st century skills, and they are known as learning skills, literacy skills, and life skills, as you can see on the screen. There are 4 learning skills. They are named as 4 C's: the critical thinking, creativity, collaboration, and communication. There are 3 literacy skills identified by CBSE Ministry of Education. They're known as IMT, the information literacy, media literacy, and technology literacy. And the most important, the life skills. They're known as FLIPS. There are 5 life skills identified by Ministry of Education: flexibility and adaptability, leadership and responsibility, initiative and self-direction, productivity, and social and cross-cultural interaction. My dear teachers, my dear friends, these 21st century skills are very, very important to develop among the learners. And we should plan our lesson every day to inculcate, to develop the value system as well as the 21st century skills among the children. To achieve the vision of National Education Policy 2020 and to achieve the desired learning outcomes, the CBSE has defined certain curriculum objectives. The first one is the teaching learning process should aim for 360-degree holistic development. The role of teacher is not to provide the information to the children. Our role is not limited to provide the knowledge to the children. The aim of teaching learning process should be 360-degree holistic development. That includes 21st century skills along with the great Indian value system. The children in the classroom and outside the classroom must be given enough opportunities to construct the knowledge rather than rote memorization. We should discourage the rote memorization in classroom as well as outside the classroom. The children must be allowed to construct the knowledge. The children must acquire essential skills and competencies to develop problem-solving skill and decision-making skill to solve the real-life problems. My dear friends, as respected Dr. A.K. Sharma sir said yesterday, that we are to make our children resilient, make them resilient. If somehow they face failure in their life, they must be capable of standing again. To make children resilient should be the aim of education. Along with it, they must have a decision-making skill so that they can take the right decision in their life. They must have a problem-solving skill to solve the real life problems. Imparting knowledge is just a drop in the ocean in an education system. The teaching learning process include innovative pedagogies such as experiential learning, art integrated learning, toy-based learning, storytelling, gamification, ICT integrations. So these are the different innovative pedagogies which are suggested by CBSE to all schools across Pan India. And we, the teachers, have responsibility. We have duty to follow the instructions of CBSE. We are to inculcate these innovative pedagogies in day-to-day teaching learning process. Only then we will be able to achieve the vision of NEP 2020. My next slide is on syllabus versus curriculum. We all teachers in the beginning of session always look on the syllabus. That is the topics to be finished across the session. We hardly look at the curriculum. Syllabus as I said earlier, it's just a drop in the ocean. The curriculum is ocean. The curriculum is an holistic approach towards obtaining desired learning outcomes with the help of conducting various n number of activities within the classroom as well as outside the classroom. To finish the syllabus is not the objective of education. We are to perform the various type of activities within the classroom as well as outside the classroom. And this is the only way we can prepare our future citizens. This is the question paper design as issued by CBSE. My dear friends, if you look at this design, you'll find that about 68% of the questions will be asked from low order thinking skills. What are low order thinking skills? I will be discussing with you the Bloom's taxonomy. 68% questions will be there to test their low order thinking skills, whereas 32% of the questions will test their higher order thinking skills, which are known as competency-based questions. So we are to provide instructions to our children. We are to decide our learning outcomes, learning objectives, all assessments, formative as well as summative, in such a way that can develop low order thinking skills as well as higher order thinking skills among children. So every learner in the classroom should have ability to respond to the questions which are based on loads as well as HOTS. So we need to understand first the question paper design before deciding or before planning a lesson in the classroom. My dear friends, to achieve the vision of NEP 2020 and to develop the required competencies as described in the question paper design, the key tool is, the significant tool is Bloom's taxonomy. So before planning any assessment, any lesson, we need to understand the Bloom's taxonomy. My dear friends, all question papers at all the levels, from school to CBSE and to JEE NEET, all levels are designed as per the Bloom's taxonomy. Here on the screen, you can see the 6 cognitive levels of Bloom's taxonomy, from simple to complex, from concrete to abstract. These 6 levels of cognitive domain, that is the thinking skill, will help all the educators to decide their learning objectives, their learning outcomes, their question paper design. And if we follow this Bloom's taxonomy 6 levels while planning a lesson, while planning any assessment, our children will do wonderfully well. And in that way only we will be able to achieve the vision of NEP 2020. The simplest level in Bloom's taxonomy, that is the cognitive domain, the thinking skill, is the knowledge, where the questions are based just to recall the informations, definitions, the units, and then comes understanding, that is the comprehension. So when we ask from our children, describe this, explain this, we are actually asking the questions based on understanding. And next is the application, where the children are able to apply the knowledge they have learned in the classroom on unknown situations. Draw a diagram, solve the numerical problem. These questions belong to the application level. Knowledge, comprehension, or understanding and application. These three levels are called as low order thinking skills. 68% of the questions in 10th standard board examination will be based on these three thinking levels. It's knowledge, understanding or comprehension, and application. And then comes higher order thinking skills: analysis, evaluation, and creation. The remaining 32% questions will be based on analysis, evaluation, and creation ability of the learners. In analysis, what we do? We split a concept in the micro parts. The splitting of a concept into micro parts is analysis. Write the properties of metals, write the properties of a bar magnet, write the properties of magnetic lines. So these are the questions which are based on analysis. Assertion, reasoning questions are based on analysis. And then comes a very important evaluation. My dear friends, evaluation questions develop decision-making skill among learners. In evaluation questions, the children need to take a decision. The children need to justify their decision also. The questions where decision is required. Which one is best? Which one is better? Which would you select? So first, what do? You compare the two concepts, and on the basis of comparison, we take a decision. So evaluation thinking skill develops decision-making skill among children, and then becomes the highest level of cognitive domain. That's a creation. So what are creation-based questions? We'll discuss in the later on also. The creation-based questions are the questions where you need to use two or more than two concepts. The children need to integrate two or more than two concepts to generate a new concept. In these questions, the children will be given an unknown situation where they need to apply more than two concepts to solve the problem. So when we plan a lesson, my dear friends, make it sure that your learning objectives, your learning outcomes, all assessments are aligned with Bloom's taxonomy. And these are the suggestive learning outcomes as per Bloom's taxonomy. These are not the ultimate. These may change from teacher to teacher, from topic to topic. So these learning outcomes define the questions which are based on their remembering skill, understanding skill, applying skill, analysis skill, evaluation and creation skill. So it is not mandatory to define the learning outcomes which can touch all the 6 levels of cognitive domain. You can touch 3, you can touch 4. But at least try to take one learning outcome from the higher order thinking skill. Maybe analysis, maybe evaluation. And if it is possible in a particular topic, you can take the learning outcomes, you can plan the learning outcomes, you can decide the learning outcomes based on all 6 levels of cognitive domain. Now let's begin with today's topic, that is the magnetic field due to current carrying conductors. The previous knowledge required to understand this topic is what is magnetic field? What are magnetic lines? And before coming to this topic, the children must have learned what is magnetic field, what are magnetic lines, due to a bar magnet. A bar magnet is a permanent magnet. And what is the magnetic field? Magnetic field is the space around a magnet, the region around a magnet where its effect can be experienced. And what are magnetic lines? Magnetic lines are nothing but imaginary pictorial representation of magnetic field. It's a pictorial representation of magnetic field around a magnet. And in case of a bar magnet, if you can see the figure here, this is an animated diagram of the magnetic lines and magnetic field around a bar magnet. And you can see in that diagram that the magnetic lines are directed from north to south pole outside the magnet. And within the bar magnet, these magnetic lines are directed from south to north. So it is very clear, it is crystal clear that the magnetic lines make closed loops. So it must be clear to the children that the magnetic lines make closed loops. And at any point, if we want to find out the direction of magnetic field, there are two options. In first option, we can place a magnetic needle there. You can see this magnetic needle here in my hand. So you can place the magnetic needle there. And the direction in which the north pole of the magnetic needle would point, that would be the direction of magnetic field. And the second point is that we can draw a tangent at that particular point. The direction in which the tangent is aligned, that would be the direction of magnetic field at the given point. No two magnetic lines can ever intersect. This must be clear to the children. And the magnetic monopoles do not exist. The isolated magnetic poles do not exist. The north is always associated with the south pole. So this is the previous knowledge which is expected to be there before beginning with the topic. My dear friends, Orested was the scientist who laid the foundation that a current carrying conductor behaves as a magnet. Before 18th century, the electricity and magnetism were used to be the different phenomena. Even though some sailors, while traveling, had found that whenever the lightning strikes their ship, the magnetic compass in their ship gets deflected in the different direction. It means before 18th century also, some of the sailors have noticed this thing, that atmospheric electricity has ability to deflect the magnetic needle. But they did not notice it. So before 18th century, it was believed that electrical forces and magnetic forces are distinct forces. They are different forces. In July 1820, Danish scientist Christian Oersted accidentally discovered a relationship between electricity and magnetism while demonstrating the heating effects of electric current in a classroom. Oersted noticed that when he turned on an electric current by connecting a cell with the wire, the compass needle held nearby deflected away from the magnetic node where it normally pointed. So Oersted accidentally found that a magnetic needle placed close to the current carrying conductor is able to give deflection. If the magnetic needle is giving the deflection, it is crystal clear there is a magnetic field around it. And there was no source of magnetic field around that magnetic needle. Hence, the Oersted concluded that the source of magnetic field is the current carrying conductor that was placed very, very close to the magnetic needle. Although that deflection was very weak, but the Oersted knew that something significant has happened. It means the world came to know about the new branch of physics, and that is called as electromagnetism. So there is a crystal clear relationship between electricity and magnetism. So you can see in the diagram to the extreme left side, the magnetic needle is placed below the current carrying conductor. And the north pole of the magnetic needle is giving the deflection towards east. And in the middle diagram, you see the same magnetic needle is now placed above the current carrying conductor. And now the north pole of the needle is giving the deflection towards west. So this is clear now that above the current carrying conductor and below the current carrying conductor, the direction of magnetic fields are different. They are opposite to each other. And to the extreme right, you can see the diagram. It's an animated diagram. You see one compass needle is above the current carrying conductor and one compass needle is placed below the current carrying conductor. So when the current is passed to the conductor, both the needles are giving the deflection in opposite direction. The red part is showing the north pole, the black part is showing the south pole. You see their red parts are getting deflected in the opposite directions. So magnetic field is there above as well as below the conductor. But the direction of magnetic field is 180-degree opposite to each other. The direction of deflection of magnetic needle can also be found by using Ampere's swimming rule. So we can tell our children that they can apply the Ampere's swimming rule to find the direction of deflection of magnetic needle. The rule says that if a man is swimming in the direction of current, means his head is pointing in the direction of current, then the north pole of the magnetic needle placed above the current carrying conductor would be deflected towards his left hand. But if the same man is swimming below the current carrying conductor, then the north pole would be deflected towards his right hand. And this rule can also be remembered as the term snow. And what does the snow mean? The snow means that if the current is flowing from south to north of the magnetic needle, then the north of the magnetic needle would be deflected towards west. So if the current is from south to north, then the north of the magnetic needle would be deflected towards west. So with the help of Ampere's swimming rule or the snow rule, the children will be able to find out the direction of deflection of magnetic needle when it is placed above or below the current carrying conductor. Now it's a time to think, my dear friends, does magnetic field produced by a current carrying conductor depend on the shape of the conductor? I need your responses. What do you think? Does the magnetic field produced by a current carrying conductor depend on the shape of the conductor? So you can see in my hand, there are three types of conductors, if you could see. It's a straight conductor. It's an insulated copper wire. It's a straight conductor. It's a circular coil. You can see it's a circular coil having few turns. The circular concentric turns. It's also a conductor. And this is a helical coil, also called a solenoid. So I have three different types of conductors: straight, circular, and helical. What do you think? In all three cases, we will have same magnetic field, or different magnetic field. So when I say magnetic field, it means both magnitude as well as direction. I need your responses, my dear friends. If they are physics teachers today, please respond to this question in yes or no.
Yes, sir, it will be having different magnetic fields, different shaped magnetic fields.
So yes, good. So it is clear after looking at this slide that the magnetic field produced by a current carrying conductor does depend on its shape. In the first diagram, you can see, in the first figure, you can see we have a straight conductor. It's a current carrying conductor. And in the second case, we have a circular coil. In the third case, you can see we have a helical coil called as a solenoid. In all these three cases, you can see the pattern, the strength, the direction of the magnetic field is different. So it is very clear to us now that the magnetic field produced by a current carrying conductor depends on the shape of the conductor also. So first of all, we will discuss the magnetic field due to an infinitely long current carrying straight conductor. My dear friends, before I proceed with this topic, I just want to discuss with you one point, and that is called as inclusive education. This is very important point, inclusive education. It's a very broader term, but I will discuss with you only one aspect of the inclusive education, and that is differentiated instructions. See, in a classroom, we have slow learners, we have gifted learners. So it is the responsibility of the teacher, it's the responsibility of the mentor to cater the needs of both type of learners, slow learners as well as gifted learners. The gifted learner in a classroom are those children who are highly focused, logical, and they normally participate in the various type of competitive exams. Like NTSC, we used to have NTSC, and a various type of Olympiads. So it means for gifted children, we cannot limit our learning objectives to the NCERT textbook only. We need to go beyond the NCERT. So in today's session also, I will be discussing with you some additional informations related with the current topic. So I hope you won't mind it and you won't put the message in the chat box that this is not the part of the syllabus, this is the deleted syllabus. Because the gifted students need some more informations apart from the NCERT text. So today I have included the additional informations also, which you can provide to the gifted children. So let's come to the session again. The magnetic field due to an infinitely long current carrying straight conductor. After Oersted experiment, it was concluded that a current carrying conductor acts as a source of magnetic field. It was also found later on that magnetic field due to current carrying conductor depends on the various factors, including the shape of the conductor. So let us consider a straight conductor in the form of an insulated copper wire. And for experiential learning, we can pass this straight conductor to the center of a thick cardboard sheet. And the two ends of the wire are connected with the cell with the help of a rheostat and a key. The rheostat is a variable resistance. It can be used in the circuit to change the magnitude of the current. So when we switch on the circuit, the current starts flowing through the straight conductor. And we place a magnetic needle very close to it. we'll find that the magnetic needle is giving the deflection, and deflection in the magnetic needle shows the presence of magnetic field around the current carrying straight conductor. If we sprinkle iron filings randomly on that thick cardboard sheet, and we tap the cardboard sheet gently, we will find that the iron filings arrange themselves in a specific pattern. And if you look at the diagram there, that specific pattern is concentric circles. And the center of all circles lie on the wire. So it means the magnetic lines around a straight conductor are in the form of concentric circles, where the center of all circles lie on the wire. It's time to think again. I need your responses. Please give your responses. What do you mean by infinitely long straight conductor? What is an infinitely long straight conductor? If I say this few centimeter long conductor is infinitely long, then on what basis I'm saying this is infinitely long, although it has a finite length? So this point must be clear to the children in the classroom teaching. Why, on what basis I'm saying this is infinitely long? And why there is need to tap the cardboard sheet after sprinkling the iron dust on it? Why do we tap it? Why the instructions are there in the experiment also that we need to tap the cardboard sheet? I need your responses, my dear friends, physics teachers. Please give your response.
Iron fillings will adjust themselves according to the magnetic field of the straight long conductor.
See, the answer to first question is the infinitely long straight conductor is that conductor whose length is much larger as compared to the perpendicular distance of the observation point from the straight conductor. It means the point where we are calculating the magnetic field is lying very, very close to the straight conductor. It means the L, that is the length of the conductor, is much greater as compared to small r. Here, small r is representing the perpendicular distance from the current carrying conductor. So in that sense, the conductor is infinitely long, even though it has a finite length. The answer to second question is why there is a need to tap the cardboard sheet. We tap the cardboard sheet due to two concepts. First, to overcome the inertia. We will have to transform the inertia of rest into inertia of motion. And second is to overcome the force of friction. Unless or until you overcome the inertia and the force of friction, the iron filings won't move under the effect of magnetic field. So these two basic informations must be conveyed to the children in the classroom teaching while discussing this topic. Now, this slide represents how we can find out the direction of magnetic field at a particular point around a straight conductor. At any point where you want to find out the direction of magnetic field, place the magnetic needle. You can see in the animated diagrams here. So when you place the magnetic needle at a particular point, the magnetic needle gives the deflection. The direction in which the north pole is pointing, the direction in which the north pole of the magnetic needle is getting deflected, is the direction of magnetic field at that particular point. So you can see in both the diagrams, when the current is passed through the conductor, all magnetic needles placed around it are getting deflected. And you see the pattern in which they all are getting deflected. अगर मैं सभी पॉइंट्स को मार्क करके ज्वाइन करूं, I would get a circle. So this again proves that the magnetic lines around a current carrying conductor are in the form of concentric circles. Now, we have seen this thing that the magnetic lines around a current carrying conductor are in the form of concentric circles. Now, the next issue is, are these circles clockwise or anti-clockwise? And to find the direction of magnetic lines around a current carrying conductor, whether they are clockwise or anti-clockwise, we can use right hand thumb rule, which you can see in the diagram here. The right hand thumb rule says that if we hold the current carrying conductor in our right hand in such a way that the thumb is pointing in the direction of current, then the direction in which the fingers of the right hand are getting curled will be the direction of magnetic lines. So it is crystal clear from this diagram, from this rule, that if the current is vertically upwards, then the magnetic lines would move in the anti-clockwise direction. But if you see, if the thumb is vertically downwards, means the current flowing through the conductor is vertically downwards, then you see the direction in which the fingers are getting curled. This is a clockwise direction. And when the thumb is pointing vertically upwards in the direction of current, you see the direction in which the fingers are getting curled. This is the anti-clockwise direction. So this is a very simple rule given in NCERT textbook, which the children can apply to find out the direction of magnetic lines around a current carrying straight conductor. There is another rule that's called as the Maxwell's corkscrew rule. And that has the same application. This is also used to find out the direction of magnetic lines around a current carrying straight conductor. And the rule says that if we rotate the screw in such a way that its tip is pointing in the direction of current, then the direction of rotation would be the direction of magnetic lines. So it means if the screw is rotated anti-clockwise, my dear friends, if the screw is rotated anti-clockwise, then its tip always points in a vertically upward direction. When the same screw is rotated clockwise, its tip points in a vertically downward direction. So you can show a screw in the classroom, right-handed screw, and keeping the screw in the right hand, try to rotate it in the front of the class, clockwise or anti-clockwise direction, and see in which direction its tip is pointing. So that would also, this rule would also help the children to find out the direction of magnetic lines around a current carrying straight conductor. Now I have used an ICT pedagogy here to represent the magnetic field pattern around a current carrying straight conductor. In the first diagram, you see the current is flowing in a vertically upward direction. And the magnetic lines around this current carrying conductor are in anti-clockwise direction. In the second diagram, again, you see when the current is switched on, you look at the deflection of the magnetic needles. Look at the pattern of the deflection of magnetic needles kept around the current carrying conductors. That pattern is resembling like a circle. And then you see in the middle diagram, when the current is flowing through the conductor, the magnetic needle kept above and below the current carrying conductor are showing the deflection in opposite direction. And fourth and fifth, again you see the current is flowing, and look at the pattern of the magnetic lines. They are in the form of circles. So we can show this picture in the classroom with the help of smart boards. We can share this ICT pedagogy with the class through the class groups. The children will be able to understand, they will be able to analyze the concept of the current carrying conductor, how they produce the magnetic field around it, what is the pattern, what is the direction. So there are so many factors which affect the magnetic field due to a current carrying straight conductor. If we increase the strength of the current flowing through the conductor, you see the magnetic compass placed near the conductor gives a very strong deflection. If the strong deflection is appearing in the magnetic needle with the increase in the strength of the current, this clearly shows that the magnetic field is directly proportional to the strength of the conductor, the strength of the current flowing through the conductor. So as we move away from the current carrying conductor, the deflection in the magnetic needle becomes poorer and poorer. The magnetic needle gives a very weak deflection when it is kept far away from the current carrying conductor. So this clearly shows the magnetic field is inversely proportional to the distance from the conductor. And my dear friends, this distance should be taken perpendicularly. So it is clear that magnetic field of a current carrying conductor depends on the two factors. One is the current flowing through the conductor. Another is the perpendicular distance from the current carrying conductor. And if we remove the proportionality, you look at the slide. If we remove the proportionality, we get a constant here, which is mu naught by 4 pi. Now, this is an additional information which you can provide to the gifted children in your classroom. That the constant here is mu naught by 4 pi. Now, what is mu naught? This mu naught is called as permeability of the free space. Now, what is permeability? It is the ability of a medium. It is the ability of a substance to allow the magnetic field to pass through it. Permeability represents the extent up to which a substance can be magnetized. And the value of this mu naught is 4 pi into 10 raised to power minus 7. You can give this information to the students who are gifted, who are focused, and who need the additional information. And the next conductor is a circular coil, a current carrying circular coil. My dear friends, every elementary part of a current carrying circular coil produces a magnetic field. And the magnetic field produced by every elementary part of a circular coil gets added up at the center. So the magnetic field that we actually get at the center is the sum of magnetic fields produced by every elementary part of the current carrying conductor. We can show the similar activity. We can perform the similar activity as we did in the straight conductor. We can take a straight conductor, we can fold it into a circular loop whose two ends are passing from the two holes made on a thick cardboard sheet. And if we join the two ends of that circular wire with the cell with the help of a rheostat and a key, and we place a magnetic needle close to the arms of the circular wire, what do we observe? That the magnetic needle gives the deflection. So that shows the presence of magnetic field around a current carrying circular coil. So you can see these are beautiful diagrams representing the pattern of magnetic lines around a current carrying circular coil. In the first diagram, you see when the current is passed to the circular coil has few turns. See how the magnetic lines are formed and how the iron dust is getting arranged. You look at the first diagram. the iron dust present on the cardboard is getting arranged in the form of concentric circles. And look at one more thing. These circles are becoming larger and larger as we move away from the current carrying portion of the circular coil. So this clearly shows that in case of a circular loop also, the magnetic lines are in the form of concentric circles. And as we are moving away and away from the part of the current carrying coil, the circles are becoming bigger and bigger. Look at the center. In the second diagram or the third diagram, look at the center of the current carrying coil. The magnetic lines are almost parallel to each other. So that clearly shows that in the middle, at the center of the current carrying coil, the magnetic field is uniform. My dear friends, the parallel lines, make it clear to the children in the classroom, the parallel magnetic lines represent a uniform magnetic field. Now, how can we find out the direction of magnetic field at the center of a current carrying circular coil? To find the direction of magnetic field at the center of a current carrying circular coil, we have right hand rule. So what does this right hand rule say? The rule says that if we curl the fingers of the right hand in the direction of current flowing in the circular coil, then the direction in which the thumb of the right hand would point would be the direction of magnetic field. I again repeat, we are to hold the circular coil in such a way that the fingers of the right hand are pointing in the direction of current. And you see, if the current is anti-clockwise, then the thumb is pointing in the perpendicularly outward direction. And if the current flowing in the coil is clockwise, the thumb is pointing in perpendicularly downward direction. So it means the direction of magnetic field in case of a current carrying circular coil is perpendicular to the plane of the coil. This is very important information which needs to be told to the student in the classroom, that the direction of magnetic field in a current carrying circular coil is perpendicular to the plane of the circular coil. And one very important point here, as I told in the beginning of this session, the isolated poles do not exist. The magnetic monopoles do not exist. My dear friends, when the current flows through a circular coil, the circular coil behaves as a complete magnet. So when we say complete magnet, it means its one face is behaving as a north pole and other face is behaving as a south pole. Now, how can we find out that which face is acting as a north pole and which face is acting as a south pole? And for that, we have a clock rule, and that is called as a clock face rule. And according to this rule, if we stand in front of a current carrying coil and we look at the direction of current, if the direction of current is anti-clockwise, look at the diagram here. If the direction of current is anti-clockwise, then that face of the circular coil would behave as a north pole. And if the direction of current in that particular face is clockwise, that face would behave as a south pole. So looking from one face, if the current is anti-clockwise, that face would be north pole. And looking from the opposite face, the direction of current would be clockwise and that would behave as a south pole. So current carrying circular loop is a complete magnet. It's a complete dipole having north and south polarity. My dear friends, let us watch this video. This is a beautiful video that would explain to you that how a current carrying circular coil behaves as a magnetic dipole, how it produces the magnetic field, how can we find the direction of that magnetic field, and what is the pattern of magnetic lines around a current carrying circular coil. It's a beautiful video of about 6 minutes. Please focus on it.
Magnetic field due to a current carrying circular coil. We have already studied that when current is passed through a straight conductor, a magnetic field is produced around the conductor. This region of magnetic field can be represented as concentric circles around the wire. So we can say that a cylindrical shell of magnetic lines of force surrounds the entire conductor. The direction of these lines of force can be found by the right-hand thumb rule or Maxwell's corkscrew rule. Both these rules can be verified with a compass needle also. Now, modify the straight conductor to form a circular loop and pass it through the two holes in a cardboard. Connect the ends of the coil and a rheostat in series. Sprinkle some iron filings randomly on the cardboard. Switch on the key of the circuit and adjust the rheostat to allow a current of about 2 amperes to pass through the conductor. It can be seen that the directions of the current flowing through each arm of the circular loop are mutually opposite. Now, as we gently tap the cardboard, we can see that the iron filings align themselves in a specific pattern. They are in the form of circles around each arm of the conductor. These circles prove the presence of a magnetic field. To find the direction of these magnetic lines of force, we apply the right-hand thumb rule. According to this rule, we can find that the direction of the magnetic lines of force around the arm of the conductor with upward flow of current is anti-clockwise, while that around the arm of the conductor with downward flow of current is clockwise. In other words, as the direction of the current in each arm of the conductor is mutually opposite, the direction of the magnetic lines of force is also opposite to each other. Conversely, within the space enclosed by the coil, the lines of force are in the same direction. Let us study the various properties of the magnetic field produced due to the current carrying circular coil. Observe that the lines of force are circular near the arms of the conductor. But as we move from the arms towards the center of the coil, the lines of force become almost parallel to each other. Thus, near the center of the coil, the magnetic field may be considered to be uniform. Hence, it can be said that as the distance from the center of the conductor increases, the magnetic field intensity decreases. At the center of the coil, the magnetic field is maximum and is directed perpendicular to the plane of the loop carrying current along its axis. Next, increase the current flowing through the conductor from 2 to about 6 amperes and tap the board gently. We can see that more iron filings get aligned with the magnetic field lines. That is, the number of magnetic lines of force increases as the magnetic intensity increases. Now, increase the radius of the coil. You can see that the magnetic field intensity decreases. The magnetic field produced around the coil proves that the coil behaves like a magnet and has a north and south polarity. The clock rule is used to find the polarity of a current carrying coil. If we look at this particular face of the coil, we can see that the current is flowing in an anti-clockwise direction. Moreover, the magnetic lines of force emerge out of this face of the coil. Hence, this end is said to be the North Pole. Similarly, looking from the other side of the coil, the current is found to be flowing in the clockwise direction. The magnetic lines of force enter into this phase of the coil. Therefore, this phase is considered to be the south pole. Hence, the clock rule states that when looking at one particular phase of the coil, if a current is found to be flowing in an anti-clockwise direction, that phase of the coil is considered to be the north pole. If the current flows in the clockwise direction, that phase of the coil is considered to be the south pole. Summary. A magnetic field is produced around a circular coil carrying current. The direction of these magnetic lines of force can be found using the right-hand thumb.
So, my dear friends, I hope you have liked this video and that made the concept of magnetic field around a current carrying coil very clear. So it is very clear from this video that the magnetic field produced by a current carrying conductor in the shape of a circular coil depends on the two factors. One is the current flowing through the conductor, circular conductor. Another is the radius of that circular loop. So if we combine these two, we get the magnetic field at the center of a current carrying circular conductor is directly proportional to I upon R. And if the children ask from you that what will happen if we remove the proportionality and gets a constant here, what will be the value of that constant? So you can provide an information to your students in the class that that constant is actually here in this particular case mu naught by 2, where mu naught is again the permeability of the medium. To what extent the medium can be magnetized, that is the meaning of permeability. And the value is 4 pi into 10 raised to power minus 7. If the circular coil has n turns, then every turn will produce an equivalent magnetic field at the center in same magnitude as well as in same direction. So therefore, the net magnetic field at the center would be the sum of magnetic fields produced by all the n turns. And as a result, the net magnetic field at the center becomes mu naught Ni upon 2R. And next we have the magnetic field due to a current carrying long solenoid. So what is a solenoid? A solenoid consists of an insulating long metallic wire closely wrapped in the form of a helix. A long solenoid is that whose length is very, very large as compared to its radius. When a current is passed through the solenoid, then each turn of the solenoid can be regarded as a circular loop. You can see here, my dear friend, this is a solenoid. This is a helical coil. See, it consists of a very large number of circular turns. Every circular turn will have its independent magnetic field. And at any point, if you find the magnetic field, that would be the sum of magnetic fields produced by all the circular turns present in this helical coil. Every single circular turn will have its own magnetic field. If there are 10,000 turns, let us suppose, then there will be 10,000 magnetic fields at one particular point. And the net magnetic field would be the sum of all the magnetic fields. My dear friends, let us watch a very short video to get an idea of the magnetic field lines pattern around a current carrying helical coil or a solenoid. It's a very short video that will describe the pattern of magnetic lines around a current carrying helical. The See how the iron dust is getting arranged. The field around a current carrying solenoid looks similar to that of a bar magnet. So see the beautiful diagrams here representing the magnetic field due to a current carrying helical coil or a solenoid. It's a very important topic in 10th standard science. As I told you that at any point, the net magnetic field is the sum of magnetic fields produced by all the circular turns present in the solenoid. It has been observed that outside the solenoid, these magnetic fields cancel each other. These magnetic fields oppose each other. As a result, outside the current carrying solenoid, the magnetic field is very, very weak. And for practical purpose, we take it as zero. But inside, in the interior of a current carrying solenoid, all these magnetic fields add up. As a result, we get a very, very strong and a uniform magnetic field inside the current carrying solenoid. If you look at the diagram here, these are animated diagrams. If you look at the first diagram, you will find that inside the current carrying solenoid, the magnetic lines are almost parallel to each other. The magnetic lines is a very important question in 10th standard physics. If the magnetic lines are parallel in the interior of a current carrying solenoid, it represents that the magnetic field there is uniform. So in the interior, in the middle of a current carrying solenoid, there is a strong magnetic field which is almost uniform. And one very peculiar property here, that this magnetic field resembles the magnetic field due to a bar magnet. Now, the many students may ask this question, that why the magnetic field of a bar magnet is similar, is equivalent to the magnetic field of a current carrying helical coil. My dear friend, there is a beautiful video. Watch this video and you will come to know that why and how a current carrying solenoid is equivalent or similar to a bar magnet. This will make the concept clear. It's a beautiful video, my dear friends. Look at this.
Saw that if you have an electric current carrying loop, then it generates a magnetic field that's very similar to that of a bar magnet. But it doesn't quite resemble a bar magnet, because if you look inside the bar magnet over here, then you can see that there is this long region where the magnetic field is pretty straight. It's not exactly straight, but pretty much straight and parallel to each other. Can you see that over here? However, if you look at our artificial magnet over here, then notice that this region where the magnetic field lines are straight is very short. And so this resembles not a big bar magnet, but a very tiny bar magnet. So now the question is, how do we create something that generates a magnetic field perfectly like a large bar magnet, where we have a large region where the magnetic field lines are pretty straight inside? That's what we should find out now. So how do we do this? Well, what if we bring in another current carrying coil? Another current carrying coil and place it down here somewhere. Then it's identical to this one, so it's going to produce an identical magnetic field of its own. And I'm going to show that in a different color over here. But remember, so you know what's going to happen? The two magnetic fields are going to merge together, and give us a new magnetic field that's going to look somewhat like this. Ooh, look at the combined magnetic field. We now have a straight region over here. We also have a straight region over here, but in between it's kind of bulky. So how do we straighten this out? Well, I'm pretty sure you can guess now. Let's add one more current carrying coil in between over here, and let's see if it straightens out. So if we introduce another current carrying coil, again, it's going to generate its own magnetic field, which I have shown in another color. And I'm pretty sure it's looking like a mess right now. But again, the magnetic fields don't ever intersect. So now this magnetic field will merge with the previous magnetic field. And together, the magnetic field of all the three coils together is going to look somewhat like this. Hey, look at this magnetic field. We're getting close to what we want. But again, we have these little bulging out regions. We have little wings over here. And I'm pretty sure you know what to do next. Well, just keep adding more and more coils in between. So you know what? Let's go crazy. Let's say we add 50 coils in between. I'm not going to show all the 50 coils. I'm just going to show only a few one. But let's imagine we add something like 50 coils. I'm pretty sure you can guess what's going to happen. The magnetic field inside is going to become almost straight now. And these regions are also going to straighten out. And so the new magnetic field of all these coils together will look like this. And ta-da! We have done it. This looks exactly like what we wanted. So if we have lots and lots of current carrying coils, then it resembles a bar magnet. Now, of course, to make this construction easier, instead of taking different loops and keeping it on top of each other, we could take a single wire and then coil it like a spring to give us multiple loops. Somewhat like this. See, we've taken a wire, you coil it multiple times and pass current through it. And since we're getting a magnet due to electric current, we call such magnets electromagnets. And this particular electromagnet, which has a shape like a pipe or a tube because of so many coils, we give it a name. It's called a solenoid. And the word comes from German, Solen, which means pipe, and oidus, which means shape. So whenever you coil something so much that it looks or resembles like a tube or a pipe, we tend to call it a solenoid.
So I hope you have liked this video. And now we will be able, after watching this video, we will be able to answer to our children that why a current carrying solenoid is equivalent to a bar magnet in terms of the magnetic field pattern. The magnetic field produced by a current carrying solenoid at a point in the interior, not outside. I told you that outside magnetic field is very, very weak. At a point in the middle is directly proportional to the current flowing through the solenoid and the number of turns per unit length. So when we say number of turns per unit length, it means the number of turns present in a unit length means 1 meter length of the solenoid. So the number of turns per unit length can be obtained by dividing the total number of turns with the length of the solenoid. So the expression for the magnetic field becomes that B is directly proportional to Ni upon L. And again, if we remove the proportionality, we get a constant here, and that constant is mu naught. So the magnetic field intensity, the magnetic field strength present at any point in the interior of a current carrying solenoid is given as mu naught Ni upon L. My dear friends, the NEP 2020 calls for a shift from an assessment system that is summative and which is basically test the rote memorization skills to one that is more regular and formative, that is more competency based, promotes learning development for our students, and test higher order skills such as analysis, critical thinking, and conceptual clarity. It means we need to plan such assessments after every lesson, which can develop higher order thinking skills among our children. The children must become critical thinker. They must become creative. They must become resilient. They must have decision making skill, problem solving skill. So assessment questions should not be based merely on rote memorization. And this is an assessment as planned by me for today's session, which is based on Bloom's taxonomy. And there are the questions which are based on remembering skill. There are the questions which can test their understanding skill. There are the questions you see which test their applying skill, analysis skill, evaluation, and creation. So we, the mentors, we, the teachers, have a responsibility to develop low order thinking skill as well as higher order thinking skills among our children. And this is the only way we can justify the vision of NEP. Thank you. So if you have any question, any query, you are most welcome.
My dear friends, do ask me questions. If you have any query.
Okay, thank you very much.
My sincerest regards to
our mentor, Dr. A.K. Sharma, sir.
Thank you very much. Today's session was wonderful. First session was taken by Dr. Gurpreet Kaur. It was very nice, although I belong to the subject, but I have thoroughly enjoyed. There are many things which are beautifully explained, and
Thank you, sir.
it is the way the teacher should strike the chord, because many concepts are there which are not there in the NCERT, as Mr. Hartinder also said. So what is the characteristic feature of a good teacher is that we should not confine to the textbook. We should go beyond the textbook, make the version simplified for the students and give them so that they should know. And Dr. Gurpreet Kaur has well explained the mystery of the life. Beautiful presentation.
Thank you, sir.
The chapter was also very good introduction. And the second session was Mr. Hartinder. I was looking to the chat box. Some of them was saying that it is a very good session, very descriptive, very elaborative. And he has explained various concepts related to this magnetic field. And it was supported by the videos and by the diagrams. So I think that the concepts should be very clear to the teachers. Sometimes when we teach in the class, some concepts are missing, some links are missing. So in case any such problem you are facing, it is the right platform to discuss all these things, not only about this chapter. If you have any problem about any other chapter, you can freely talk to us at the last. So thank you very much, Mr. Hartinder Sharma and Dr. Gurpreet Kaur.
Thank you, sir. Thank you so much.
You are superb. Thank you.
Thank you, sir.
And
Yes, sir.
now it's your turn.
Thank you, sir. Thank you so much, sir. So my sincere thanks to the resource persons. It was a lovely session, very well explained and informative. So we should end the session today, conclude with the Shanti Mantra.
ॐ पूर्णमदः पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ॐ शान्ति शान्ति शान्तिः हरिः ॐ श्रीगुरुभ्यो नमः हरिः ॐ
Thank you so much. So can we just leave the session? So I request the teachers to please leave the session. Our next resource person for the day. Mr. Hartinder Kumar. PGT Physics